resisted motion. So whenever a body is moving through a medium like air or water, it's subjected to a resistance in the opposite direction that it's moving. And this resistance is a force that's acting in the opposite direction. So let's learn a bit of terminology just before we begin. So we've got retardation, which is acceleration acting in the opposite direction. We've got to know about terminal velocity, which is the maximum velocity that an object will reach after it's... So if an object is falling from a really high distance, it's going to reach a maximum velocity, and this velocity is called the terminal velocity. The faster an object is moving, the more resistance it experiences, and the resistance that it experiences, let's call it R, is usually equal to, it's usually proportional to the velocity. So we can say that the resistance is proportional to the velocity by some power of the velocity. Usually we might use just the velocity to the power of 1 or the velocity to the power of 2 for the resistance. And let's have a look at a couple of scenarios. So if we have an object on the ground, we're going to be looking at horizontal motion, and whatever way it's traveling, let's say it's moving in this direction with a velocity v, that's the direction we want to define as the positive direction, and we want to define its starting point as the origin. So here we would define x is equal to 0, and it's anything pointing to the right in this case, since it's moving to the right, would be considered positive, and anything to the left would be considered negative. So if it was moving in this direction, the resistance experience would be acting to the left, and here we'd have some weight on the body, that's mass times gravity, and some normal force as well. So these are all the forces experienced. It's important to know that the velocity is not a force experienced on the body, and that's why I've drawn it above the diagram, not a part of the force diagram there. We could also have a body moving vertically. If it was moving in a downward direction, downwards would be considered positive, and we'd have our weight force acting down and our resistance force acting up since it's moving down. But if that vertical body was moving up with a velocity, the resistance would be acting down and the weight force would also be acting down. And the positive direction we need to take is up since it's moving up. Let's have a look at an example. So we're going to have an object that's going to be starting from rest and dropped from a height of 1,000 meters. We're going to have, it's going to be dropped to the ground from a height from 1,000 meters. And this object is going to be of unit mass, which means it's going to be 1 kilogram. And there's a couple things we want to find. We want to find the velocity squared in terms of x, and the speed before it hits the ground, or the speed just before it hits the ground. And here we know that the resistance is equal to 0.004 times the velocity squared. So let's go ahead and add our forces into our diagram. So we know we have a weight force, acting downwards. The weight force is always acting down, and it's equal to mass times gravity. And mass is just equal to 1, so we just get 1 times gravity for our weight force. Then we also have the resistance acting upwards, since we know the motion is in a downwards direction, since the velocity is acting downwards. So the resistance we know is equal to 0.004 times v squared. And remember, we're always our starting point, we're referencing as x equals 0. And since downwards is going to be the positive direction because it's moving, this point down here at the ground is actually going to be x equals 1,000. So it's a very common mistake to let that equal minus 1,000 since it's 1,000 lower than this point, but since direction is positive in this direction, this point is positive 1,000. Now, we've got our two forces acting on the body. So here we can write an expression for the sum of the forces in the y direction. So we know that the sum of the forces in the y direction is going to equal mass times acceleration in the y direction. We have two forces. Remember, downwards is positive, so that means our gravity force is going to be positive, and our resistance force is going to be negative, so we get minus 0.004 v squared. And they're the only two forces in the y direction that we need to add up. Equals mass times our acceleration. Mass is 1, and acceleration we'll just write as a. Might just flip this around. So a equals g minus 0.004 v squared. And we're after an expression for v squared in terms of x. Since we have acceleration as a function of velocity, we want to rewrite our acceleration. And we want an expression for x, so the best choice to rewrite our acceleration would be to use v times dv dx for our acceleration, and this will equal g minus 0.004 v squared. Let's go ahead and divide both sides by v, so we get dv dx equals g minus 0.004 v squared all over v. We don't want to integrate both sides just yet because we have dx on the bottom and this is not in terms of x. So we're going to take the reciprocal of both sides. So we're going to get dx over dv equals, so this should be just a v, not a v squared. So we're taking the reciprocal, so we're going to get v over g minus 0.004 times v squared. And now we can go ahead and take the integral of both sides. Now, we'll plug our initial conditions in for our displacement and velocity, so we don't end up with any constants. So initially we're at 0 for our displacement, and we're going to get to some displacement x. And then initially we have 0 velocity and we're getting to some final velocity v. So the integral of dx dv is just going to be x between 0 and x. And this is going to equal, now integrating this, we know the derivative of the denominator is actually going to be minus 0.008 v, and it's pretty close to what we have in the numerator. So let's put it up, we know we can multiply by this, so 0.008, but then we need to divide by minus 0.08. So we're going to put that out the front. So it'll be timesing this by minus 1 on 0.008. So this is going to give us, well, minus 1 over 0.008. Then the integral of this just becomes the natural log of the absolute value of g minus 0.004 v squared, bound between 0 and v. So let's go ahead and sub some of these values in. So subbing x into x gives us x, and minus subbing in 0 in for x gives us 0. Now 1 over 0.008 is 125, so we get minus 125 times, we've got to sub in v first, so we get the natural log of the absolute value of g minus 0.004 v squared, subbing in v for v, minus, we've got to sub in 0 for v, so we get minus the natural log of the absolute value of g minus 0, and let's go ahead and tidy this up. So we get x equals minus 125 outside of the natural log of the absolute value of g minus 0.004 v squared minus just ln of the absolute value of g. Now we have the difference of two logs, so we can combine them as a log of a quotient. So we get x equals minus 125 times log of the absolute value of g minus 0.004 v squared all over g. And now we just need to go ahead and make v squared the subject, because we're asking for the question was asking for v squared in terms of x. So now we're going to go ahead and make v squared the subject. So let's divide both sides by minus 125. So we'll get minus 1 on 125 x equals the ln of the absolute value of g minus 0.004 v squared all on g. Then we're going to make both sides the powers of e. So we're going to have e to the minus 125x equals e to the ln of the absolute value of g minus 0.004 v squared all on g. The e and the ln will cancel out. So we get g minus 0.004 v squared all on g, all absolute valued, equaling e to the minus 125x. We can remove the absolute value by adding in a plus or minus on the other side. So we'll get g minus 0.004 v squared all on g, equaling plus or minus e to the minus 125x. Let's multiply both sides by g. So we're going to get g minus 0.004 v squared equals plus or minus g e to the minus 125x. Let's minus g from both sides. So we get minus 0.004 v squared equals minus g plus or minus g e to the minus 125x minus 1 on 125x. Let's divide both sides by minus 0.004. So we get v squared equals minus g plus or minus g e to the minus 125x all over minus 0.004. And we can tidy this up a little bit. So we can say the v squared, let's get rid of that minus at the bottom. So the minus will make that a plus, and minus with the plus or minus keeps it as a plus or minus. So we get g plus or minus g e to the minus 1 on 125x all over 0.004. And now we need to figure out which case we need. So when we know when x equals 0, v also equals 0. So plugging in x equals 0, we get e to the 0, which is 1, and we get g plus or minus g all over 0.004. We need this to be 0, so that means we need to take the negative case to make the numerator 0. And then the denominator of 0.004 we can bring up into the numerator and make it 250. So we get v squared equals 250 times g minus g e to the minus 125x for the final expression for the velocity squared. Then finally for part 2, we're after the speed just before it hits the ground, and all we need to do then is sub in x equals 1000 to work out the speed just before it hits the ground. So we'll do that over here. So remember we had v squared equals 250 outside of g minus g e to the minus 125x. And getting the speed before it hits the ground, all we need to do is sub in x equals 1000. So that's what we're going to do. So we have v squared equals 250 outside of g minus g e to the minus 125 times 1000. We get v squared equals 250. We might factor out the g while we're here. We get 1 minus e to the minus 1 on 125 times 1000 is just minus 8. And we'll get v squared equals 250g. We'll tidy this up. We'll write 1 as e to the 8 on e to the 8 minus, now e to the minus 8 is just 1 on e to the 8. They have the same denominator now, so we can make it all one fraction. So v squared will equal 250g outside of e to the 8 minus 1 all over e to the 8. And finally we can square root both sides, and we'll get v equals plus or minus root 250 can be written as 5 root 10, and we'll include the g in the root, and we'll include the numerator in the root, e to the 8 minus 1, but then the denominator we can write as e to the 4, since we've got e to the 8 all to the half. And this is our final velocity just before it hits the ground, and we can actually just take the positive case since we're defining downwards to be positive. So we get our final velocity as 5 root 10g outside of e to the 8 minus 1 all over e to the 4. So let's have a look at another question involving horizontal motion with resistance this time. So here we've got a body moving horizontally of unit mass, so the mass is equal to 1 kilogram, and a resistance force equal to V plus V cubed. So this means we can draw our forces in. We know we've got some weight force, which equals mass times gravity, so 1 times G, which is just G, and a normal force. So if we define the motion as going to the right with some velocity, this means resistance will act to the left, and this will be the force of V plus V cubed. So this resistance force was in newtons. And they're the only forces on our diagram. We're also given some initial conditions. Initially, when t was equal to 0, we're at the origin, so x equals 0, and the initial velocity was given as q, where q is greater than 0. So now let's go ahead and then the question is asking for, we want to find a velocity as a function of time. And since we're after the velocity as a function of time, we're really interested in this force here, so it makes sense to sum the forces in the x direction. So we know summing the forces in the x direction is equal to mass times the acceleration in the x direction. And there's only one force in the x direction, and it's acting to the left, and we've defined the motion as acting to the right, so this force is negative. So we've just got to be careful to throw it in a bracket because there's more than one term. So we get minus v plus v cubed. That's the only force to sum, and this equals its mass times, which is just 1, times the acceleration in the x direction, which we'll just write as a. Now, let's move the negative to the other side. So we just get minus a equals v plus v cubed. And we want to rewrite a using one of the many definitions for a. And we'd like to rewrite a as dv dt. And we'll factorize out of v. We get 1 plus v squared. And the reason we chose dv dt is because we have this force in terms of velocity, and we're after velocity with respect to time as a function of time. So this brings v and t in. We want to integrate both sides, but we have this dt on the bottom, which we need this to be dv. So let's just take the reciprocal of both sides first. So we get minus dt over dv equals 1 over v outside of 1 plus v squared. And now we're ready to integrate both sides. But when we do that, this fraction over here is tricky to integrate. And now we can use partial fractions to decompose this fraction. So we're going to get 1 over v outside of 1 plus v squared equals, we've got our factors of v and 1 plus v squared. On the linear factor, we know we're getting a constant, and the quadratic factor, we're getting a linear term, so we get bv plus c. Let's go ahead and multiply everything by the denominator on the left-hand side. So we get 1 equals a outside of 1 plus v squared plus bv plus c, all multiplied by v. If we let v equal 0, this term will all go away. That'll just be 1, and we get a equals 1. We get a equals 1 by letting v equal 0. Now we know that a equals 1, so you get 1 equals 1 plus v squared. Let's expand that v out, so we get plus bv squared plus cv. Let's group our v squareds, v's and constants. So we get v squared outside of 1 plus v plus cv plus 1, and equating the appropriate coefficients. Since there's no v squared or v over here, these coefficients have to be 0. So we know that 1 plus b equals 0 and c equals 0, so b has to be minus 1. And now we can rewrite this fraction as 1 over v plus b is minus 1, so we get minus v, and c is 0, so that's gone, over 1 plus v squared. And now we're ready to integrate. So we get the integral of minus dt on dv is just minus t equals the integral of our decomposed fraction, which is 1 on v minus v over 1 plus v squared. with respect to v. So we get minus t equals the integral of 1 on, we can do these integrals separately. Integral of 1 on v is just the natural log of v, all absolute value, minus, now here we've got the derivative of the bottom being 2v, but we've only got v, so we can put a 2 here and multiply it all by a half. So we're going to get minus a half, the natural log of 1 plus v squared, all absolute value, and we're going to get our constant as well. So let's find the value of that constant using our initial conditions. We know when t is equal to 0, v is equal to q. So we know 0 equals ln of the absolute value of q minus a half times ln absolute value of 1 plus q squared plus our constant. Now, we were given that q is greater than 0, so we know it's positive. So taking the absolute value of this q is just going to give us q, and q squared is always positive. Positive plus 1 is always positive, so this term is always positive, so you can remove the absolute value there. And let's take everything to the other side. So we're going to have c equals a half ln of 1 plus q squared minus ln q. Now, the half we can bring up using our log law into this power, and a power of a half means square root. So we're going to have c equals the log of the square root of 1 plus q squared minus log q. Then the subtraction of two logs is going to be the log of a quotient. So we're going to have c equals the log of the square root of 1 plus q squared all on q for our constant term. So let's go to a new page. So plugging this back in for c, we're going to get minus t equals the natural log of the absolute value of v minus a half times the natural log of the absolute value of 1 plus v squared plus the natural log of the square root of 1 plus q squared all over q. And we're trying to get v as a function of time. So we're trying to make v the subject here. So from here, we're going to bring this half up into the power and take the square root. So we're going to get minus t equals the natural log of the absolute value of v minus the natural log of the absolute value of the square root of 1 plus v squared plus natural log of the square root of 1 plus q squared on q. Here we have the difference of two logs, so we're going to have the log of a quotient. So we get minus t equals the log of the absolute value of v over the square root of 1 plus v squared plus the log of the square root of 1 plus q squared all on q. Here we have the sum of the logs, so we're going to have the log of a product. There's going to be minus t equals the log of the absolute value of v all over the square root of 1 plus v squared multiplied by the square root of 1 plus q squared all on q. And we've brought everything into one log, so that means now we're going to make both sides the powers of e. So we're going to take our left-hand side and make that a power of e, and the right-hand side to the power of e. The log and the e will cancel out. So we're left with the absolute value of v over the square root of 1 plus v squared times the square root of 1 plus q squared, all on q, equals e to the minus t. By definition, we can know that everything in the absolute value could be plus or minus. So that means we're going to have v over the square root of 1 plus v squared times the square root of 1 plus q squared, all on q, equals plus or minus e to the minus t. We've got a lot of square roots and the plus or minus, so squaring both sides will get rid of a lot of things. So we're going to square both sides. So now we're going to get v squared over 1 plus v squared, so the square and the square root will cancel out, times this square root will cancel out as well, so we get 1 plus q squared over q squared. Now, squaring a plus or minus will get rid of it because it will always make it positive, and we get e to the minus 2t. Let's multiply both sides by this whole denominator. So we're left with v squared outside of 1 plus q squared, so that numerator on the left hand side, equals q squared times 1 plus v squared times e to the minus 2t. Let's expand both sides because we're trying to isolate for v. So we're going to have v squared plus v squared q squared equals q squared e to the minus 2t plus q squared v squared e to the minus 2t. Let's bring all our v squared terms together. So we'll take this term to the left hand side. Going to get v squared plus v squared q squared minus q squared v squared e to the minus 2t equals q squared e to the minus 2t. Let's factorize out v squared. So we're going to get 1 plus q squared minus q squared e to the minus 2t equals q squared e to the minus 2t. Let's go ahead and divide both sides by this bracket. So we're going to get v squared equals q squared e to the minus 2t all over 1 plus q squared minus q squared e to the minus 2t. And finally we can square root both sides and we'll get v equals plus or minus the square root of q squared e to the minus 2t over 1 plus q squared minus q squared e to the minus 2t. And we can tidy this up a little bit. If we say v equals plus or minus, we can root the numerator, saying it's q e to the minus t over the square root of 1 plus q squared minus q squared e to the minus 2t. We know that, so we would need to know whether to take the positive or negative case. And we know initially the velocity is equal to q. So let's go ahead and sub t is equal to 0 in. So we get v equals plus or minus q e to the 0 over the square root of 1 plus q squared minus q squared e to the 0. These are just 1. Q squared minus q squared will go, and we're left with v equals plus or minus q1 root 1, which is 1, and we know that needs to be positive, so we need to take the positive case only. So the final answer for v is q e to the minus t over the square root of 1 plus q squared minus q squared e to the minus 2t.